Welcome, everybody. I'm going to present a talk which is entitled A Globally Convergent Adaptive Velocity Observer for Non-Holonomic Mobile Robots Affected by Unknown Disturbances. This is a joint work between Jose Guadalupe Romero, David Navarro Alarcón, Haoji Kue, and myself, Emmanuel Nuño. In this work, we consider a second-order torque-controlled non-holonomic robot which exhibits constant disturbances. We design a novel adaptive observer via immersion and invariance technique, which we use to estimate the velocities and the disturbances. We prove that the estimation error converges globally and asymptotically to zero. The setup that we consider then is a second-order non-holonomic vehicle for which the kinematic description is given by this expression here, and the dynamics are affected by a constant disturbance. We would like to design an observer for these systems in order for us to estimate the linear and the angular velocity, considering that we have constant disturbances. So what we do first is that via a change of coordinates, we can rewrite these systems as a decoupled, angular and linear velocity second-order systems, that which is written by using the non-holonomic restriction plus a new definition of the inputs. So by using this definition of the inputs, we would like also to estimate the constant disturbances which are given by these two expressions here. So the rest of my talk and the main objective of this work is to design an adaptive observer for these kind of systems, for which we can globally find an estimation of the linear and the angular velocities. And also, we would like to find an exact estimation of both disturbances. So, in this work, we assume that we can measure the angular position and the linear position. The main proposition of this work reads as follows. If we consider the non-holonomic vehicle, which is given by the second-order expression that I've given you before, then if we design the adaptive velocity immersion and invariant estimators, such as following these two expressions, where subindex I means integral, we would like to design the estimations using an integral term plus a proportional term. So the integral terms are given for the linear angular velocity using these two expressions, and for the estimation of the disturbances by these last two expressions. Additionally, in the design of our adaptive observer, we have a scaling dynamic factor which satisfies this expression. We use this scaling dynamic factor in order to dominate some cross terms that appear in the Lyapunov function design, as will become clear later. So we prove and we ensure that this observer, for all initial conditions, ensures that the error between the linear velocity and the linear estimated velocity, the angular error velocity, and all the errors in the system asymptotically converge to zero. So the proof goes as follows. If we replace the estimations in the open loop second order dynamic systems, then we will arrive to two decoupled systems. One for the angular velocity term, which is given by this closed loop system here, for which, for its stability analysis, we employ a typical quadratic Lyapunov function, which of course we can show that its time derivative is negative definite along the trajectories of the closed loop system. So the angular estimation error and the error of the estimation of the disturbance that enters in the angular velocity channel, we prove that using this Lyapunov function that the origin is globally asymptotically stable. For the linear part, the closed loop dynamics of the estimation error satisfy this expression here, for which we can see that matrix AV, which is the fundamental matrix of this linear expression here, of this linear differential equation here, is a Hurwitz matrix. So what we're going to do now is to design an scaling dynamic factor such that we can dominate this term using this scaling factor here. So after replacing the dynamics of the scaling factor and after applying this change of coordinates, we will arrive to this virtual dynamical system for which if we employ the quadratic Lyapunov function that is given here in this expression, then we can show that the time derivative of this quadratic function along the closed loop trajectories together with the dynamic scaling factor will have a negative, will be negative semi-definite. In fact, by doing this, we can show that all the errors are bounded and they belong to L2. So the proof is finished by employing Barbalat's lemma. I'm going to give you now some simulations, and we have two different simulations. One, which is an open loop simulation for which we only apply the estimation of linear and angular velocities, for which we consider a disturbance in the linear and on the angular velocities which follow this figure here. So in this slide you can find all the necessary information for the adaptive observer design, for all the gains, and for the physical parameters of the non-holonomic vehicle. So the results are pretty good, for which we can show that this figure here stands for the error on the linear velocity, and the figure here reads for the error on the angular velocity, which of course has an exponential decaying term. In this time instance here is where the different disturbance appear, and after a transient we can see that the estimation converges to zero. This is the behavior of the estimation of the disturbance, which asymptotically converges, in fact exponentially converges to the real disturbance that is employed in the simulations. Then we apply a proportional derivative controller, for which instead of using the linear and the angular velocities, we employ the estimations of the linear and the estimation of the angular velocity. This controller is a PD controller which exhibits a time varying term, which is persistently exciting the angular velocity in order to satisfy Brocket steering, because the system that we're working with is non-holonomic. So this term here stands for a persistency of excitation term. So if we replace in the controller the linear and the angular velocities with the estimations that we have found using the INI velocity observer that we reported here, we can see that the error on the positions globally asymptotically converges to 0, but more important is that the estimation of the linear and the angular velocities also globally and exponentially converges to 0. Here in this last figures, we can see the dynamic behavior of the estimation of the disturbance. So, as a conclusion, in this work, we have reported a globally convergent adaptive velocity observer with known input disturbances. We have shown through Barbalat's lemma and using Lyapunov theory a rigorous Lyapunov stability analysis. And through simulations, we have seen that if we have time-varying disturbances, we can see that the observer is also robust. As a future work, we would like to extend our work to the case in closed loop with the PD controller that we have seen in the simulations. And we have also ported the INI observer for the multi-agent case. I thank you all for your attention.